Hello and welcome to another session on data mining. Today we are going to talk about generative machine learning or generative models for machine learning. But before we talk about what exactly those are and how are they different from the other models that we've talked about, let me take a higher level look of what exactly do we do in machine learning. So if you think of data that you have for a machine for your training a machine learning model, then that data is typically generated by nature or a physical process. So, for example, if you're getting scans or images of patients, X-rays, and everything, there's a there's a physical process taking outside, and we are getting samples from that process. Now, those samples are typically passed on to an oracle or some labeling mechanism which generates the labels for those examples. So, for example, if we have an apple, we take a picture of it. The process xi that generates xi is the process of taking the picture and nature producing the apple in the first place. And then we are, as objects, calling it the label, assigning it a label that is an apple or an orange. So there's a probability density involved over here as well, and there's a probability density involved over here as well. So the nature, you can think of the data generation process as being sampled, as generating samples based on a probability distribution of X. So let's say if you think about COVID and non-COVID patients, you can think of nature producing people and their data. So the generative process that produces these are can be captured in this probability distribution X. Okay, and then we have a label assignment process. We do a test, for example, which given a particular sample assigns a label to that particular example. In this case, if the example is non-COVID, we expect that it would assign a positive, negative label to that. And if the person has COVID, then we are going to assign, or this object over here assigns a positive label to that. But this is also it's a conditional probability distribution. So this object generates a probability or a label. It has a certain probability of generating a certain label. For example, y is equal to 1 given x, based upon what x is, and we also have the same thing of y is equal to -1 given x. Okay, and that's where the labels come in. So there is a label assignment mechanism and there is a data generation mechanism, and both of them are what give you your training samples and your test samples as well. So this is, you can think of this whole process of what's happening in the real world as your data generation mechanism. Okay, and you get samples from this data that you can then use for your training. You can get a number of samples. Let's say you get L samples in total. Based on this, you have a d-dimensional feature representation for each of those x's, and you have corresponding label assignment with that. And you use that, or you use this data set that is provided to you to generate or to produce a machine learning model, so that that machine learning model, when given a novel x from nature, you see this x, it is able to produce a label at test time. So this whole process, these three blocks are all there is to it when we talk about machine learning methods. So this picture is taken from a presentation by Vladimir Vapnik on the statistical theory of learning, and in my opinion, it covers all the bases of how the data generation process takes place and how we use data generated from this process to train our machine learning model, and then we can get a label. So if you have an example X that has just been obtained from nature, may not be a part of your training data. The goal is to generalize to these unseen cases to produce correct labels, so that the labels that are generated actually agree with the label assignment or the label generation process, and if the sample comes from the process that generated the data. Okay, so if a sample has been generated using P of X, what we want to do is we want to build a machine learning model that allows us to model essentially this part of the label generation process. Now, we have done that using discriminative learning approaches in which, let's say, you have got training data, you have got these images, for example, and their corresponding labels. Here's another image, you've got a corresponding label, and so on. And what we want to do is that we want to generate a machine learning model that trains to produce correct values of these parameters or weights, so that if I give it a certain x, I get a prediction. So if I give it an input x, so this is my x, I can get a prediction. Such models are called discriminative models because they can discriminate between different classes. Remember, we started our discussion on discriminative or discriminants, linear discriminants, and those were essentially functions that allow us to separate between different classes. And we extended the same idea to other types of classification problems, multi-class classification problems, for example. And a similar idea is used typically in regression, except that our labels are not discrete, and in regression they are continuous. And for example, if you're trying to predict age based on a person's mugshot, okay, so that is what is called discriminative, or what are called discriminative models. Now, if you think about these, you put in your x as input, and they produce a label at the output, right? And this can be thought of as a process in which we are doing label assignment. However, this particular machine learning model does not generate, or is not able to generate, examples. And that is where generative and discriminative machine learning approaches differ. Discriminative approaches can do label assignment, they can do regression like this one. In generative processes, what we want to do, or in generative machine learning models, what we want to do is we want to use the training samples that we have, all of the x that we have, and we want to design a machine learning model which, when given some random input, generates a sample so that that sample is no different from the samples that are given to us in the training samples. Okay, so this machine learning model generates an example, and you can do it in a conditional manner as well. We'll talk about that later. But here the goal is to generate data, not just discriminate data. So you are generating examples so that those examples follow the same probability distribution as the original data generation process, which is P of x. So you have now a real world P of x. So I'm going to call it P real, which is the nature part of this, or this part that is generating these examples. And what you want to do is you want to develop another probability distribution, or you want to learn another probability distribution, which is parameterized by some parameters theta, so that I can generate examples. And ideally, both of these are, we want that both of these have a high level of alignment, or the distribution that is learned by our machine learning model, or by our generative machine learning model, is close to the real world generation process. Now it sounds a bit complicated, but let's break it down. Let's say if you got the classic example of a head or tail, right? Now what you have is a probability distribution which is 0.5. So probability of getting x is equal to head, is 0.5, and the probability of getting a tail is 0.5, right? So now if you sample from this distribution, we can expect that 50% of, if you take a large enough sample size, you end up with 50% heads and 50% tails. So that's what this actually means. So the generative process is such that you end up with 50% heads and 50% tails. But if the generative process had been a bit different, or had it been a weighted coin, we might have had, like, we can get more heads and lesser tails in a given number of trials, right? So you can have a generative process that is, in this case, can be a biased coin. Now let's say if I give you a data set in which you have you have the outcome of those trials, okay? I give you a certain number of these, and I want you to generate samples from the same distribution from which this data came from. Okay, so you can do that by simply calculating what is the number of heads and what is the number of tails within this particular sample that had been given to you for training or for learning. And let's say you see that in this particular sample that was given to you, so I'm going to call it PS, the probability of observing a head is 0.3, whereas the probability within this sample of observing x is equal to tail is 0.7. So it's more probable to generate tails rather than heads. Okay, as we can see, there are more tails over here in comparison to heads. Now, once you have this probability distribution with you, you can use this probability distribution to generate data, or you can generate samples from this probability distribution by a simple sampling process. So when you, for example, generate random numbers in Python, you can use that process to generate samples in a in a manner that agrees with the samples that had been given to you. And what you would have done is essentially generative machine learning. You observed some parameters, or you calculated some parameters based on some observations, and now you have a way of generating examples based on those numbers. So that is a very simple model of a generative machine learning, or a very simple generative machine learning model, or a very crude one. You have a real world distribution that you want to model, and you want to model it using only a set of samples. So you only get a certain number of samples for you to be able to learn these parameters of your model, so that you can use that model to generate data, and that generated data should follow the same distribution as the real world data generation process. Okay, so let's take a more elaborate example. Let's say this plot, let's try to first analyze and study this plot. This is a very simple plot of MNIST, and this is a UMAP representation of that. So you got two axes, UMAP1 and UMAP2. Remember, UMAP is a simple visualization scheme or data dimensionality reduction scheme that can be used to visualize data. So MNIST, the fashion MNIST dataset is a dataset composed of different type of clothing items and accessories, and each of them is represented in an image. And what we have done over here is reduce the dimensionality of that image to 2 dimensions so that we can view it in 2 dimensions. So for example, this shirt over here, I'll probably need to zoom in, or you'll probably need to zoom in to see that this is a shirt, but take my word for it for now. And it has a certain u1 value and a certain value along this axis. So you can use PCA for the same thing. What we are trying to do here is visualize the distribution of examples that are present within this fashion MNIST dataset. And you can see that there are different types of shirts here, there are shoes in this region, and then you can have different type of handbags, for example, and so on, and everything. You can see that this is the sort of a lower dimensionality visualization of the real distribution of your data. So what we see over here is, let's say if I have a generative machine learning model and that I use to generate examples, so those examples are now going to be images. And what I would expect is that those generated examples follow the same distribution as I see within this plot. So as we can see over here, there is a higher density of shirts within this region. Okay, so let's say we've got a shirt over here. I'm going to call it shirt number 1, and I'm going to call it shirt number 2. Okay, so let's call this shirt 1, and let's call this shirt 2. Now we already have samples for shirt 1 and shirt 2 in our training data set. But let's say what if I want to generate a new type of shirt that lies on this manifold, or this line connecting these two points. And we can do that using a generative machine learning model. And what I would expect is that if my generated example is over here, then it should be similar to one of the training examples that is already given to me. So to summarize, generative machine learning models allow you to generate examples, not just discriminate them. They can be used, there are some variants that can be used as to classify as well, like discriminate. So they are not unsupervised. We are trying to use the existing data in order to learn the density of our data set. So you've got a real world process that generates this probability distribution. So we have a p real of x, and what we want to do is we want to model that either explicitly or implicitly so that I can use it to generate examples using a machine learning model. Okay, so let's say you've got a shirt over here, for example, and you've got a shirt over here, and let's say your generative process generates a shirt over here or some object over here, and because this lies on this particular, or it lies closer to these examples, these two examples that were given to me in the training set, I would expect that generated example to be similar in appearance to these two. Okay, so I hope now you have an idea of what generative machine learning models do. They essentially generate examples. So we can generate examples by doing density modeling. By density, I mean the probability density. So I have told you that the real data generation process has an underlying very high dimensional data density that it uses to generate examples or spits out examples and throws them at the labeling machine, which then assigns them a label, right? So this density, the real world density, actually models the probability of observing a given point x. So what is the probability that an example in my dataset would lie over here? Okay, so that's what we model when we talk about probability density. What are the chances that an outcome that I'm going to have comes out to be heads? Okay. Once I have an explicit or implicit probability distribution model, so we have a real world distribution, and what we want to do is to use samples that are given to us to learn a model of that distribution, either an explicit model or an implicit model. In an explicit model, we have parameters that can control different factors involved in that distribution, whereas in an implicit one, we simply have a process that generates examples that are able to that follow the same distribution as the real world distribution. So once I have an explicit or implicit distribution p of x, I can sample from the distribution to generate an example. The goal is how to learn p of x. We can use a neural network to generate an example that produces p model x of theta. So theta would be the weights of the neural network, and you can generate examples that should follow the same distribution. So if you relate it to our previous concepts about partitioning of the feature space, when we discussed classification, I told you that all machine learning models, what they do is they partition the feature space into different areas. A general form of that description is that we are trying to model the density of different type of objects. So for example, you've got all shirts over here, and you've got, let's say, shoes over here in this region. Now I can draw these boundaries just as I've done on the screen, and that gives you an idea of what regions show a high density of a certain type of object. So density modeling is actually the same thing as partitioning the feature space. If you can do one thing, you can do the other. Except that density modeling is more richer, because when we are trying to partition the feature space, we say that, okay, here is where the boundary of one class or one concept ends, and here is where the boundary of the other concept begins. Whereas in density modeling, what we are doing is we're assigning probability values to each point within our feature space. So the probability of observing any point over here is 0, because there we don't have any samples, at least for this particular problem. There are no samples over here, but then we have got a bunch of samples over here, which are all shirts. So what we would like to have is a model. When we are trying to do generative modeling, we would like to have a model that generates a probability distribution or that generates samples that follow the exact same probability distribution like this one. Okay, so a very simple way of thinking about this is you've got a natural process that generates samples, right? So there are apples being produced in nature, and they have a certain color, and then you have oranges that have a certain color, right? And nature has a certain way of modeling that. Let's say if we capture two properties of these objects, and let's say we want to capture the weight of these objects, these fruits, on the other axis, then what we would have is a density plot, much like the one that you see on your screen, and you would have different types of objects placed at different locations within that density plot. There would be an area occupied by apples, and then ideally there would be an area occupied by these oranges. Now, if we want to generate images that follow the same distribution, or we want to build a machine learning model that follows the same distribution, what we really want to do is we want to have a process that generates images so that I cannot discriminate between the distribution, the real distribution, and the distribution of samples that my generative model has given me. And that is what we really want to do in generative machine learning. Now, we've taken a look at various type of machine learning models, but in terms of generative modeling, we have what we want to do is to build a machine learning model to approximate a data distribution. So let's say we have got these real world samples, these ones, and they are coming from this data distribution, p data of x, and these are images, as you can see. And what we want to do is we want to design a machine learning model which can generate images like this one, so that they have a probability distribution p model of x. And what we really want to do is we want to have this probability distribution similar to the data distribution, or the generative process, or the distribution of the generative process in real. Okay, so this density estimation is a core problem in unsupervised learning, and there are two different types of flavors. Either you can have an explicit density estimator, or you can have an implicit density estimator. So in an explicit density estimation process, what you want is you want to develop a formulation that gives you a probability estimate for a given sample x. Okay, so you essentially end up with how likely is a particular example that I have, what's the probability of generating that example. So we have a formula for that. In the other one, we can simply sample from that distribution. We are not interested in modeling this probability distribution that gives out these probability numbers, but what we want to do is to simply generate those samples, so that those samples have p model of x is closer to p data of x, but we're not interested in explicitly calculating what the probability of a particular example is. Now, we've already covered a way of generating data with machine learning models, and that is autoencoders. So in autoencoders, what we do is we have a what is called a bottleneck neural network. So you give it your input data during training. That data is passed through the neural network layers until it reaches a bottleneck, which is a reduced representation of your data. And that reduced representation is built in such a way that it can be used for a given example. It can be used. So let's say if we got an example xi, for that we produce a feature representation zi, so that we can use this zi to generate or approximate this xi. So this is what autoencoders do, and there we can train all of the weights in these layers by trying to minimize, for a given training data set, the difference between xi hat and xi. If you think about it, if we cut this neural network in the middle over here, we can get two neural networks, right? Let's talk about this left part first. What it does is that for a given xi, it produces a zi. So it generates a lower dimensional representation for a given example, right? And ideally, what we want to do is that all the information that could be present in the input features should be captured within these what are called latent factors, or these ZIs. And once we have those code vectors, we can use those code vectors to generate a certain example. So let's say if you got an image of a shirt, for example, or a digit, we can represent it in a lower dimensional example over here. Okay, and then I can use that lower dimensional example, the lower dimensional feature representation, to generate an approximation of the output, right? Now, what this is the main idea behind autoencoders. But what if I change this zi? Let's say instead of passing the exact same thing, let's say what happens when I pass it 2.4 and 3.4 over here. You would end up with a slightly different image, right? Perhaps an 8 that looks like this or a slightly different 8. So this is a very simple, or this part over here is a very simple generative machine learning model. It may not be good for most of the applications that we are interested in, but it is a very simple generative model because we can control, or we can generate, we can change this zi, and it can generate different examples. Now, if you break this autoencoder into two parts, you can think of this part over here as learning to generate a lower dimensional representation of the data so that we have so we can compress the information that is given to us as input. On the other hand, you can think of this part over here as the decoder part or the generator part. And if zi is this reduced feature representation is a part of the data distribution of your input data. So you have got a data set and you train all of this model on using that data, then these ZIs should be able to generate images that mimic the same images that you have in your data set. Okay, as long as you sample ZI from the same distribution as your input example. So this is a very simple example of a generative machine learning model. Okay, so we've talked about this. If you break down now, so if you think about machine learning, you can have two types of models. You can have either discriminative, and you can have what are called generative models. The discriminative models that you have are can be used to assign labels, can be used to predict the class of a certain object, whereas these generative models, they can generate examples. So if you want to generate a picture of an apple, these can do that. These can determine whether this is an apple or not. So this is the primary difference between these two categories. In terms of these generative approaches, there are two major categories. One of them is explicit density estimation, and the other is implicit density estimation. So let's talk about explicit density estimation first. There are different type of methods. We haven't covered those in detail. There is density estimation. There are density estimation techniques such as these MADE or pixel RNN or CNN based methods, or nonlinear independent component analysis methods. The goal of these methods is to come up with a probability density function that can give you a probability of having a certain example. So these explicitly produce a relationship that allows you to determine what p of x would be for a given x. Okay. We've talked about autoencoders. There are certain variants of autoencoders called variational autoencoders, which explicitly model the generative process in terms of an explicit density function. Okay, so these are more refined versions of the basic autoencoder that we have talked about. There's also something called a Boltzmann machine. So it's a machine essentially that can generate samples, but it can be trained so that it models this the real world probability density function. And once we have that probability density function, we can use it to generate examples. Okay. The other category that is really picking up these days is called implicit density estimation. In these methods, all we are interested in is generating samples. We're not interested in generating or in learning a formulation for p of x. However, what we want to do is that the generated samples should have the same distribution as your original data set. So, but we don't explicitly approximate this probability density of your data set. So generative adversarial networks, which is going to be the topic of the next lecture, this is what they typically do. They try to approximate the density in an implicit manner of a given process. Okay, so we are going to talk about that next. Just to summarize, we have got two different types of machine learning models. They can be discriminative or generative. And we are in going back to this slide over here. If you talk about there's a natural process that generates data, and that data gets labeled by another object, And we use these labeled samples to learn a machine learning model, the parameters of a machine learning model, so that you can classify or regress a certain example. And this is what we typically do when we talking about these discriminative models. However, if you want to approximate a certain generative process using a machine learning model. So if you want a machine learning model that can generate images of apples and generate images of shirts, of handbags, and so on, then what you are looking for is a generative model. However, that generative model should generate samples that follow the same distribution as the real world process. So we don't want a handbag that doesn't look like a handbag, right? So that's the learning goal of these generative models. And the way they learn it is they want to minimize the differences between the real world P of X, or the probability distribution of X, and what the model has learned. So either we can do that implicitly or explicitly. We can have an explicit model of the probability distribution of X that that machine learning model learns, and or we can have an implicit representation so that the samples generated from that machine learning model now follow the distribution that we are looking for. Okay, so that's the basic process of these generative models. Next, we are going to talk about how we can develop very specific types of generative models called generative adversarial networks. Okay, thank you.